Today we're going to look at an optimization problem using linear programming techniques to solve that optimization problem. A photographic development company has determined the minimum chemical requirements for blending a developer for a particular type of film. The company is able to purchase from two manufacturers, and when they purchase, they get bags of chemicals. The bags of chemicals contain multiple units of the different chemicals A, B, and C. The table below summarizes the information with regards to what you get from a chemical manufacturer, what you pay for a bag, and how many units of the individual chemicals you need to complete a batch. So here we see for chemical A, we get 6 units of chemical A per bag of brand A, 2 units of chemical B per bag of brand A, and 2 units of chemical C per bag of brand A. So we pay $5 for that, and similar information is provided for brand B. We also notice that we need 18 units of chemical A, 12 units of chemical B, and 16 units of chemical C. Now that we understand the problem, let's look at the method we're going to use to solve it. Firstly, we're going to sketch a diagram. Then we are going to assign variables to the unknown quantities. Next, we are going to write an objective function that uses the variables that we got in step 2. Next, we're going to write constraints equations, and constraints equations are limitations we put on the values of the variables so that the problem makes sense. Next, we're going to use a mathematical software package like Excel and MATLAB and others to solve the problem. Here we see in the sketch we have multiple bags from brand manufacturer A, and we see that we've represented that you get a box of A, B, and C in each bag. We don't know exactly how many bags in total from manufacturer A we will be getting, nor do we know how many from manufacturer from manufacturer B. So we're going to say, let X1 be the number of bags from the first manufacturer, and let X2 be the number of bags from the second manufacturer. These are the two unknown quantities, X1 and X2, and we want to choose X1 and X2 so we can minimize the overall cost of developing a batch of film. Next, we write the cost objective function. The objective function is the function we're seeking to minimize or maximize or set to some certain value. In this case, we are using Z to represent that objective function, and Z is equal to $5 times the number of bags from manufacturer 1 plus $4 times the number of bags from manufacturer 2. So in total, this will be the cost of chemicals that we purchase. Note, X1 could be 0 or X2 could be 0, and in those cases we would have different costs. If X1 and X2 are 0, we will have 0 as the cost. 0 as the cost sounds like it should be the minimum. However, we have constraints that we must obey, and those constraints tell us we must have at least 18 units of chemical A, and we must have at least 12 units of chemical B and 16 units of chemical C. So what we must do is write those statements as mathematical formulae. In this case, 6 times X1 represents the number of units of chemical A we get from manufacturer 1, and 3 times X2 is the number of units of chemical A we get from manufacturer 2. And those must be greater than 18. You can check back the table to make sure that this logical statement and the ones that are similar to it make sense. We also have the fact that we cannot buy negative bags of chemicals, so X1 must be greater than 0 and X2 must be greater than 0, greater than or equal to 0. Note that they cannot be negative, and that these are basically going to be put into the system as lower bounds. Next, we have a constraint that might be a little more difficult to handle in some software packages. It is very easy to handle in Excel, and I'll show you that. X1 and X2 must be integers because we cannot buy partial bags of chemicals. So we are going to make sure that they are integers. Here we have the MATLAB code that solves the problem. Unfortunately, this MATLAB code does not ensure that x1 and x2 will turn out to be integers, but it does get you the solution in this case. And we use the function linprog, which is a MATLAB built-in function. If you wish to find a software MATLAB code that actually ensures that you get the linear programming with integer solutions, I've provided a link in the video here that you can look up. Next, we are going to look through the MATLAB code. We can see that the code is, some of the code is green, some of the code is white. The green code are comments and are not necessary for the function to run. The white code here is the executable MATLAB statement, and it makes up the MATLAB function. In this case, we say that z is equal to open square bracket 5 space 4 close square bracket. This basically says that z is going to be a function where the coefficients of x1 and x2 are 5 and 4 respectively. We know this because the first position occupied in this vector is filled with 5, and MATLAB understands that this is the coefficient of your first unknown. 4 is the coefficient of your second unknown, x2. If we had a third unknown, x3, let's say we needed $7 times x3, we would put a space after 4, and then we will put 7 there. So next we have a matrix for the left hand side of our constraints equations, and the left hand side of the constraints equations are given by, in this case, not 6 and 3, which are the coefficients of our constraints equation. If you remember, it was 6x1 plus 3x2 is greater than or equal to 18. Now MATLAB's linprog function has one limitation. You must provide the inequalities as less than or equal to inequalities. So in this case, the A matrix represents the left hand side of those constraints should they have been converted into less than or equal to inequalities. So if you take an inequality and you multiply it by -1, you flip the sign. So a greater than or equal to inequality becomes a less than or equal to inequality. So 6x1 plus 3x2 is greater than or equal to 18. You multiply that entire thing by -1, you get minus 6x1 minus 3x2 is less than or equal to minus 18. Therefore, we can write our constraints as a matrix, -6, -3, with the next line being -2, -4, with the next row being -2, -8. On the right hand side, we write the B matrix. B is equal to -18, -12, and -16, which represents the right hand side coefficients of our inequality. The next piece of code sets our lower bounds. Again, we know that the first element refers to x1 and the second element refers to x2. So by putting 0, 0, we are setting x1's lower bound to 0 and x2's lower bound to 0. Next, we make a call to the linprog function. So you will see fval exit flag output lambda is equal to linprog, and then you see open round bracket z a b open square bracket close square bracket lb. Now this particular line of MATLAB code, forgive me, there should have been an open square bracket before x, the first letter of that statement. Now when this code executes the function linprog, it will return x, a vector of solutions for x1, x2, your unknowns. Fval is the evaluated value of the function at the minimum value, using the actual values of x1 and x2 that give us the minimum cost. So fval reports that, and exit flag reports a number that tells you whether or not you have reached the optimum solution. So in order, I will show you how this is run, and then I will show you how to find what the values of output, lambda, exit flag, etc. mean. So we call the function linprog. We pass to that the z the A, the B, the right hand side of the constraints, and then you'll see these open square brackets with nothing inside it. These represent equality constraints. We have no equality constraints in this case, but let's say you had a management directive that you must purchase 2 bags from manufacturer 1 because of some contractual agreement. You can put that in here. In this problem, that will not make sense, because if you purchase a fixed amount from manufacturer 1, then you've automatically set how many you would purchase from manufacturer 2. So the next parameter is the LB parameter, and that LB being the lower bound. So we have a lower bound of 0, 0. So next I'm going to show you how the MATLAB code is run by executing the MATLAB script and show you the response you should be getting. So here we have the MATLAB script. It's basically going to be given by writing the MATLAB code in a script file. First, I'm going to clear the screen so we can see that we have no variables in the workspace. We have no variables here. In the command window, we have no data, no output in the command window. So we're going to execute the MATLAB code. And when we execute the MATLAB code, note you can see that I had the open square bracket here in the MATLAB code that wasn't copied in properly to the presentation. When we execute the MATLAB code, we can see that x means it gives us a vector 2, 2, and that vector 2, 2 represents x1 should be 2 and x2 should be 2. Fval is the value of the function when you evaluate using x1 and x2 equal to 2 and 2 respectively, and that comes up to $18. So that's our minimum cost. Exit flag 1 tells us that we have completed the problem successfully. If you want to know the values of the exit flags and what they mean, at the MATLAB command prompt, you can type doc and then type linprog, and MATLAB will launch a help window telling you exactly what the linprog program does and exactly its limitations and what the value of the different parameters mean. Now, MATLAB doesn't, as I say, solve for integers, so there's no option that I can supply that tells linprog it must supply integers as the response. And you can see these are floating point numbers, 2.0000. They're not integers. Okay, so now we will look at the solution in terms of solving in Excel, and here we can see that we've set up the problem in an Excel file, and we are going to use the solver interface in order to solve the problem, right? So I am going to now launch Excel and show you the solution in Excel. So in this spreadsheet, I set up variables for x1. So this is basically x1 here, the number of bags of brand 1. Number of bags of brand 2 is x2. And I also put in cells for the costs. So the cost of a bag of brand 1 and the cost of a bag of brand 2. In case those costs change, I can redo the linear programming problem with the new cost. And we can see how that affects the purchasing requirements. Here we have the cost function, and you can see that the cost function is the exact same function we wrote before. $5 times x1 plus $4 times x2. You can note the cell references and check this yourself. Afterwards, we have the constraints equations. The constraints equations are constraint 1, which is going to be the formula 6 times b2, so 6 times x1 plus 3 times x2. Now note, I should have made the 6 and the 3 as cells that I could change the values of, so that in case a manufacturer says you no longer get 6 bags of chemical A, you get 2 bags of chemical A, it'll be fairly easy to change and rerun the spreadsheet without going into the formulas themselves. Next, you will see these operators, greater than or equal to. This is nothing more than an indicator to the person looking at the spreadsheet what the constraint is about. It's not used in the code anywhere. In the Excel sheet, you will see on the right hand side of the inequality constraints, and you will note that we have one for each constraint. So how do we solve the problem? So let's start by saying that we don't know the solution. It's basically 0, 0. We have no idea what the solution is at this point. So the first thing I'm going to do is I'm going to go to my data menu and I'm going to check to see if I have something called solver. If I don't have solver, then I'm going to install the solver. To install the solver, you go to File Options, and when you go to File Options, you will see the Add-ins button. As you click the Add-ins button, Excel will go to the Add-ins sheet, and you will see a Go button here where you can click and you can see what additional add-ins you have installed into Excel. For me, I have the solver add-in installed. You would want to make sure this checkbox is checked and you click OK. I have it installed already, so I will begin to use it now. So to launch the solver, we click the solver button and a window comes up, and that window shows us an interface where we can enter our constraints, where we can enter our objective function, etc. So the first thing we want to do is enter our objective function. You can see that this references cell B9, and cell B9 is where our cost function was. You can also see we told Excel that it should feel free to manipulate the values of B2 and B3. B2 and B3 are basically the values that are B2 and B3 are the values of X1 and X2 that we will be changing, and you can see that when we select here that B2 and B3 are changing. Next, we're going to set up our constraints. I have preset the constraints here, but I will go into the constraints to show you how they have been set up. So the first constraint is going to be set up in a screen where you add a constraint. You will see this screen. You will provide the cell reference to the left hand side of the constraint. Here you can see I reference B12, and you can see that right now B12 holds a value of 0, but the formula is referenced here. Next, we select which type of constraint it is. We're not limited like in MATLAB, that is, we are less than or equal to constraint. We can have less than or equal to, greater than or equal to. So it's much more flexible and easy to use. And next we have the right hand side of the constraint, which we've referenced as D12, which you can see on the spreadsheet is 18. You would click Add at this point, and when you click Add, you would see that we get an extra constraint added. Right? So in this case, we've got our constraints for the 3 constraints equation. We've put a constraint for our lower bound, and that is for the number of bags of brand 1, which is B2, cell B2. Cell B3 has been constrained to be greater than or equal to 0. So we've entered our lower bounds as constraints. Next, Excel has the ability, unlike MATLAB, for you to ensure that a cell or a group of cells that you are trying to optimize will be an integer. So you can write equal to here and then select or type in integer, but the easier way to do it is to just select int here. And when you select int, Excel will repair the constraints. It will put in equal to integer. So all you do is really click it must be an integer and you click OK. So when you do that, you will have this constraint here. So let me just do it over so you will see it. So I'm going to delete this constraint that I have here, and I'm going to add back a constraint saying it must be an integer. So I'm clicking Add. I'm selecting the cell references, which is these 2 cells here. Those are the ones that we must constrain, and we want it to be an integer, and you will see Excel puts it as an integer, and I click Add, and then when I go back I will see that a new constraint has been added. With respect to the solver options, we have the GRG nonlinear solution method, and this algorithm is for nonlinear problems which are not covered in this video but can be created using advanced techniques for finding your objective function, etc. We have the simplex LP method, which is the method that we will be using. The simplex LP method uses linear programming. And next we have the evolutionary solver. The evolutionary solver you must apply lower and upper bounds for every one of your variables that must be solved, and the evolutionary solver will search the entire solution space to find a global minima or maxima depending on what you've asked for. Right? Now the linear programming problem, we've put simplex LP, and now we just have the option of clicking solve. We click solve, and you would see that as the solver works, it has set the value of the number of bags of brand 1 to 2 and the number of bags of brand 2 to 2. Now, if you want information additional to what you have been provided by just in the spreadsheet, you want to see how it came to that conclusion a little bit more, you can get an outline report, and you can click OK. And what will happen is Excel will add another sheet to the system. So I'll just do it over. Right, solve. Select the answer report, outline report, click OK. And here you will see Excel has created another sheet, and it has outlined the problem for you, telling you the cost value, the function. It's told you what is the solution for x1 and x2, what the original value was, what the final value was, and it's told you what the constraints were and whether or not those constraints were actually met or whether they were disobeyed. Right? So once you've done that, you've solved the LP problem. You can see that the MATLAB solution is the same as the Excel solution. Right? And now you're in a position to make a smarter decision from a business perspective.